What's up guys, Leon here, welcome back to Tesla on Air. Nikola Tesla invented the Tesla Coil in 1891. Since then, power electronics advanced tremendously. Today, I will show you a type of Tesla Coil that Tesla himself probably would be proud of. A pulse skip dual resonant solid-state Tesla Coil. In the past, I've built all kinds of tiny Tesla coils. And they definitely have their charm. They are relatively easy to build and fairly safe. But if you really want long, powerful sparks, there's no way around a DRSSTC. DRSSTC stands for Dual Resonant Solid-State Tesla Coil. In principle, it works very similar to Nikola Tesla's original Tesla Coil, except that instead of a high voltage transformer and a spark gap, we use an electronic inverter. The problem with a dual resonance system is this. The longer the on-time of a spark, the longer it can grow, but at the same time the current in the primary circuit increases massively. That's why classic tiny DRSSTCs usually operate with extremely short pulse width, sometimes as low as 50 to 100 microseconds. Otherwise you kill the semiconductors. In the early 2000s, a crucial idea emerged, electronically shutting down the coil as soon as a certain primary current is reached. This is called OCD, overcurrent detection. With OCD, DRSSTCs can be tuned very safely without instantly destroying the IGBTs in the inverter. The results are already impressive, but we want even longer sparks. Imagine the spark as a rectangular pulse. The current rises until the OCD triggers, and then the pulse ends. The spark collapses, but what if we didn't shut down the entire pulse and instead skipped only individual oscillations within that pulse? A single pulse consists out of hundreds of thousands of high-frequency oscillations, and with every oscillation, the primary current rises a little bit more. With pulse skipping, individual oscillations are deliberately skipped. The plasma channel remains intact during this extremely short gap and is immediately re-energized afterward. And the result? Pulse duration is no longer in the microsecond range, but in the millisecond range. There's no need to reinvent the wheel here. Schematics and PCB files are readily available online. I decided to use the EOD 2.9 driver and through-hole, mainly because it's robust and much easier to solder. The PCB was published on GitHub by the user ProfDC9. I really appreciate that. For this project I ordered my PCB from JLC PCB, and I can definitely recommend them, especially for projects like a DRSSTC. The purple is just awesome. Ordering is super easy, just upload your Gerber files and you don't even have to select the board size manually. PCBs start at just $2. If you also want a stencil, you can order the PCB and stencil on the same page. Stencil starts from $3. Just remember, if you choose a frameless stencil, you need to set the custom size yourself. The quality has been rock solid for my DRSSTC builds. Now you can easily build your own Tesla coil. I put all links in the video description down below. Before starting the build, I designed the entire coil as a 3D model in Fusion 360. This made planning much easier and allowed me to 3D print many of the parts. The whole build took me about 2 months, but it was definitely worth it. I deliberately designed the coil so that it can be fully disassembled and repaired if something fails. If you have any questions about the details, feel free to leave them in the comments. The secondary coil is wound with a 0.25 mm wire over a length of 47 cm on an 11 cm tube. The primary coil consists out of 9 turns made from 8 mm copper tubing. The system resonates at approximately 127 kHz. Commissioning a coil like this is anything but trivial. especially getting the phase lead set correctly. At this point, a big shout out to my bro Jeroen, aka Acid Boyd on YouTube. Definitely check out his channel. The heart of this coil is a full bridge made out of two Mitsubishi CM150 IGBTs. They're more than 20 years old and were originally designed for motor drivers and frequency inverters. But that's exactly what makes them extremely robust for this application. The primary capacitors are door knobs ordered from AliExpress. As an interrupter, I'm using my old DRSSTC interrupter with a few small modifications to allow for longer on times. First, I'll show you the coil running in classic OCD mode, so you have a clear reference for what pulse skipping actually changes. Switching between modes is done very easily using a jumper on the PCB. Things are about to get loud. High voltage can be extremely dangerous. Please don't attempt this yourself. Welcome to the back rooms. An endless forgotten liminal space of flickering halls and identical rooms, entered when reality glitches. The results are already absolutely amazing, but trust me guys, pulse skipping is completely different. At this power level, I can't run the coil for too long. Otherwise, the ABS spaces of the primary coil would start to melt. I think we need a higher room for the next video. You can't even imagine how loud this coil is. You don't just hear the discharges, you feel them through your entire body. It's absolutely fascinating and terrifying at the same time. You probably know that iconic photo of Nikola Tesla, right? I recreated that. Hey guys, Leon here. Yesterday I had a Tesla jam with Live and David, two bros of mine, and we pushed my DRSSTC to about 5.6 kV. That was absolutely insane, so I will definitely show you that now. Guys, that was absolutely crazy. My ears are still ringing. In theory, much more power could be extracted from this tiny coil, but that's definitely material for another video. With that being said, I hope you enjoyed the video. Feel free to leave me a comment down below. And then guys, we see us in the next video.